Extending a circuit to a new outdoor subpanel requires careful consideration of wiring ampacity and compliance with the National Electrical Code (NEC). In this scenario, the indoor subpanel is fed by a 60-amp 2-pole breaker from the main house panel, utilizing number 6 with ground wiring. The existing subpanel in the garage contains a 30-amp 2-pole breaker for an air compressor and two 20-amp 1-pole breakers, one for lights and one for receptacles. The desired addition is an outdoor subpanel to supply a future 240 volts alternating current RV receptacle, a hot tub, and an outdoor ground fault interrupter (GFI) receptacle. The core question revolves around whether it is permissible to extend the existing number 6 wiring from the garage subpanel to the new outdoor subpanel using double barrel lugs, considering the existing 60-amp protection. The short answer is no. Number 6 wiring cannot be extended to the new outdoor subpanel in this scenario. The primary reason lies in the NEC stipulations regarding conductor ampacity and overcurrent protection. The NEC mandates that the overcurrent protection device, such as the circuit breaker, must not exceed 80% of the conductor's ampacity. For number 6 copper wire, referencing NEC table 310.15b16, the ampacity is typically 55 amps, assuming it's a copper conductor rated for 75 degrees Celsius. Taking 80% of 55 amps yields 44 amps. Therefore, to comply with the NEC, the overcurrent protection device must be rated at 44 amps or less. In the proposed setup, the new outdoor subpanel will house breakers to protect individual loads, such as the RV receptacle, hot tub, and outdoor GFI receptacle. The sum of the ampacities of these breakers could potentially exceed 60 amps. If this happens, it would violate the NEC 80% rule, as the number 6 wiring, with its adjusted ampacity of 44 amps, would be subjected to a load exceeding its safe carrying capacity. To address this, several steps can be taken to ensure a safe and code-compliant installation. Firstly, upgrading the wiring to the outdoor subpanel is essential. The wiring used must have an ampacity equal to or greater than the rating of the circuit breaker protecting it, which in this case is 60 amps. Number 4 copper wire is a suitable choice, as its ampacity, according to NEC table 310.15b16, is 70 amps, again assuming a 75 degrees Celsius insulation rating. Secondly, the connection method in the garage subpanel needs attention. A double barrel lug can be installed in the garage subpanel to facilitate the connection of both the existing number 6 wiring from the house panel and the new number 4 wiring to the outdoor subpanel. Crucially, the double barrel lug must be rated for the ampacity of the larger wire, which is the number 4 wire with a rating of 70 amps. Thirdly, it is critical to ensure that all components used are properly rated and listed for their intended purpose. This includes the circuit breakers, subpanels, wiring, and connectors. Using components that are not appropriately rated can lead to overheating, electrical fires, and other safety hazards. Now, let's consider the existing loads in the indoor subpanel. The 30-amp 2-pole breaker for the air compressor and the two 20-amp 1-pole breakers for lights and receptacles contribute to the overall load in the 60-amp circuit. Before adding the outdoor subpanel, it's crucial to perform a load calculation to ensure that the existing 60-amp circuit can handle the additional load. If the load calculation indicates that the 60-amp circuit is already close to its maximum capacity, it may be necessary to upgrade the wiring and breaker from the main house panel to the garage subpanel to a higher amperage. To perform a load calculation, each load's amperage requirements need to be determined. For continuous loads, such as lighting that is expected to be on for 3 hours or more, the NEC requires that the load be calculated at 125% of its rating. For non-continuous loads, such as the air compressor, the load can be calculated at 100% of its rating. Once the total load is calculated, it must be compared to the ampacity of the circuit. If the total load exceeds 80% of the circuit's ampacity, the circuit is considered overloaded and must be upgraded. In addition to the ampacity requirements, it's also important to consider the voltage drop in the wiring. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the beginning of the circuit. Excessive voltage drop can cause appliances to operate inefficiently and can even damage them. The NEC recommends that the voltage drop in a branch circuit should not exceed 3%. To calculate the voltage drop, the following formula can be used. Voltage drop equals 2 k I d/cm, where k is the constant for the conductor material, which is 12.9 ohms for copper, I is the current in amps, d is the length of the circuit in feet, and cm is the circular mils of the conductor. For number 6 copper wire, the circular mils is 26,240. For number 4 copper wire, the circular mils is 41,740. If the voltage drop calculation indicates that the voltage drop exceeds 3%, the wiring must be upgraded to a larger size. Another consideration is the type of wiring used. The NEC specifies different types of wiring for different applications. For example, type THHN wire is commonly used for general purpose wiring, while type UF wire is used for underground wiring. It is important to use the correct type of wiring for the specific application. Finally, it is important to ensure that all wiring is properly installed and grounded. Improperly installed wiring can create a safety hazard and can even lead to electrical fires. Grounding helps to protect against electrical shock by providing a path for fault current to flow back to the source. In summary, extending a circuit to a new outdoor subpole requires careful planning and attention to detail. It is essential to comply with the NEC and to use appropriately rated components. By following these steps, a safe and code-compliant installation can be achieved. Let's further elaborate on the specific NEC articles and considerations relevant to this scenario. Firstly, NEC Article 215.2 addresses feeder conductor ampacity. This article stipulates that feeder conductors, which in this case includes the wiring from the main panel to the garage subpanel and then to the outdoor subpanel, must have an ampacity not less than the sum of the loads served, after applying any applicable demand factors. Demand factors are multipliers that recognize that not all loads will operate at the maximum rating simultaneously. For example, a dwelling unit's general lighting load is subject to demand factors, as it is unlikely that all lights will be on at the same time. However, in this scenario, the loads being added, such as the RV receptacle and hot tub, are less likely to have applicable demand factors, meaning they should be calculated at 100% of their rating. Secondly, NEC Article 240.4 discusses protection of conductors. This article mandates that conductors must be protected against overcurrent in accordance with their ampacities. As previously mentioned, the overcurrent protection device must not exceed the conductor's ampacity. This is where the 80% rule comes into play, ensuring that the conductor is not subjected to a load exceeding its safe carrying capacity. Thirdly, NEC Article 250 addresses grounding and bonding. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are at the same electrical potential, reducing the risk of shock. In this scenario, it is important to ensure that the outdoor subpanel is properly grounded to the grounding electrode system. This can be achieved by connecting a grounding electrode conductor from the subpanel to a grounding electrode, such as a ground rod or a metal water pipe. Additionally, it is important to bond all metal parts of the outdoor subpanel, such as the enclosure and the conduit, to the grounding system. This can be achieved by using bonding jumpers or bonding screws. Fourthly, NEC Article 310 addresses conductors for general wiring. This article provides detailed information on conductor ampacity, installation requirements, and other considerations. NEC Table 310.15b16 provides ampacity ratings for various types of conductors, based on their size, insulation type, and temperature rating. When selecting conductors for this project, it is important to consider the ambient temperature and the temperature rating of the equipment terminals. If the ambient temperature is high, or if the equipment terminals are not rated for 75 degrees Celsius, it may be necessary to use a conductor with a higher temperature rating. Fifthly, NEC Article 408 addresses switchboards and panel boards. This article provides requirements for the installation and construction of switchboards and panel boards, which includes the subpanels being used in this scenario. It is important to ensure that the subpanels are properly rated for the voltage and current they will be subjected to. Additionally, it is important to ensure that the subpanels are installed in a location that is readily accessible and protected from physical damage. The subpanel should also be properly labeled to indicate the circuits they serve. Sixthly, NEC Article 551 addresses recreational vehicles. This article provides requirements for the installation of electrical systems in recreational vehicles, including the RV receptacle being added to the outdoor subpanel. It is important to ensure that the RV receptacle is properly rated for the voltage and current it will be subjected to. Additionally, it is important to ensure that the RV receptacle is protected by a ground fault circuit interrupter, GFCI. GFCIs are designed to protect against electrical shock by detecting small amounts of leakage current and tripping the circuit. Seventhly, NEC Article 680 addresses swimming pools, fountains, and similar installations. This article provides requirements for the installation of electrical systems in and around swimming pools, hot tubs, and similar installations. It is important to ensure that the hot tub being added to the outdoor subpanel is installed in accordance with the requirements of NEC Article 680. This includes requirements for bonding, grounding, and the use of ground fault circuit interrupters, GFCIs. GFCIs are required for all electrical circuits within a certain distance of a swimming pool or hot tub. In addition to the specific NEC articles mentioned above, there are other general considerations that should be taken into account when extending a circuit to a new outdoor subpanel. Firstly, it is important to obtain all necessary permits before starting any electrical work. Electrical work is typically subject to local building codes and regulations, and permits are required to ensure that the work is performed safely and in compliance with these codes. Secondly, it is important to hire a qualified electrician to perform the electrical work. Electrical work can be dangerous, and it is important to have it performed by someone who is knowledgeable and experienced. A qualified electrician will be familiar with the NEC and local building codes, and will be able to ensure that the work is performed safely and in compliance with these codes. Thirdly, it is important to inspect the electrical work after it is completed. An electrical inspection will help to ensure that the work has been performed correctly and that the electrical system is safe to operate. Extending an electrical circuit involves significant considerations regarding safety, code compliance, and proper installation techniques. These considerations extend beyond merely connecting wires and include careful selection of components, adherence to NEC guidelines, and a thorough understanding of electrical principles. The selection of conductors, for instance, is not simply about choosing the right gauge based on current carrying capacity. It also involves understanding the insulation type, temperature rating, and suitability for the environment in which the wiring will be installed. Conductors exposed to direct sunlight, moisture, or extreme temperatures require specific insulation types to ensure their longevity and safety. Similarly, the choice of overcurrent protection devices, such as circuit breakers, is not limited to matching the amperage rating of the circuit. It also involves understanding the interrupting rating of the breaker, which is the maximum amount of fault current that the breaker can safely interrupt. In situations where high fault currents are possible, such as in commercial or industrial settings, it is crucial to use breakers with adequate interrupting ratings. The installation of wiring and equipment also requires meticulous attention to detail. Proper wiring methods, such as using appropriate conduit or cable types, are essential for protecting conductors from physical damage and environmental factors. Connections must be made securely and with the correct type of connectors to prevent loose connections, which can lead to overheating and electrical fires. Grounding and bonding are critical safety measures that must be implemented correctly. The grounding system provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are at the same electrical potential, reducing the risk of shock. In addition to these technical considerations, it is also important to be aware of the legal and regulatory requirements associated with electrical work. Electrical work is typically subject to local building codes and regulations, and permits are required to ensure that the work is performed safely and in compliance with these codes. It is also important to hire a qualified electrician to perform the electrical work, as electrical work can be dangerous, and it is important to have it performed by someone who is knowledgeable and experienced. Before undertaking any electrical project, it is essential to conduct a thorough assessment of the existing electrical system. This assessment should include a review of the electrical panel, wiring, and grounding system. It is also important to identify any existing electrical hazards, such as exposed wiring, damaged equipment, or overloaded circuits. Once the assessment is complete, a detailed plan should be developed for the electrical work. This plan should include a list of all materials and equipment that will be needed, as well as a step-by-step procedure for completing the work. It is also important to obtain all necessary permits before starting any electrical work. During the electrical work, it is essential to follow all safety precautions. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and working in a well-ventilated area. It is also important to disconnect the power before working on any electrical circuits. After the electrical work is complete, it is important to inspect the work to ensure that it has been performed correctly. This inspection should include a visual inspection of the wiring and equipment, as well as testing of the circuits to ensure that they are functioning properly. It is also important to obtain an electrical inspection from a qualified electrical inspector. Extending an electrical circuit to a new outdoor subpanel requires a comprehensive understanding of electrical principles, code requirements, and safety precautions. By carefully considering all of these factors, it is possible to complete the project safely and successfully. The information provided in this guide is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before undertaking any electrical work. Remember, electrical safety is paramount.